Hello everyone, my name is Arjun and I'm host today for this session. So today we have Dr. Yu from a flow cytometer core facility, and he's serving as a manager, and he has a skills to like analyze our data and all kind of flow cytometers like multicolor and probes. So he's going to speak about like a different type of like multicolor probes and like panel designs about us. So please welcome Dr. Yu. Thank you so
Great.
much. Please.
Thank you for the invitation. So today my plan is to do a demonstrate and to showing how do we handle all these potential issues to refine our data set and from the very beginning the panel design. So some of you may be already very familiar with the flow, and some of you maybe just started your career and haven't used the flow a lot. So I hope my seminar will benefit all kind of level of users. If you are fresh and you can learn some terms and prepare yourself for the future panel design, you're already very familiar. You still can learn some like lessons from the previous user, how we can improve our data settings. So that's my today's plan. Okay, so can you see my screen now?
Yeah, perfect.
That's the PowerPoint screen.
Correct. Here we go.
So the topic for today is create a clear data set for the multicolor panel. So there are two key points. First of all, we are aiming to a multicolor panel design. And second one is we want to pay attention to how do we get a clear data set. You can get any data set for the flow, but when we want to have more beautiful data, clear data. So first of all, a fresh reminder is what flow we can do. First of all is the immunotyping. Most of you are already familiar. We do like CD markers to typing different cell types and also other particle fluorescence measurements such as cell cycles. It's all use the flow form probe. We can also use the flow to measure the cytokine concentration in the solution. We can measure like up to like 20 or 30 of this at one time in one run. So we call it multiplexy cytokine panel. We can also measure the mRNA and the cell marker at the same time using a method called a prime flow. We also can measure the small particles such as exosomes, microbubbles with flow. Flow can also measure the redox status, calcium concentration, or pH value change inside the cells. So everything you can convert to either light scatter or fluorescent probe. We can use it by flow. So when you run the flow, there's some general idea you have to follow. So first of all is we want to separate negative and positive population. So the more separating, the better, of course. So when you pick the flow forms, or we call it dye, to match your antigen or your markers, we want to match in the opposite way, which means when your marker or your antigen expressed in the higher levels, you want to pick dim color flow forms. When your antigen expressed level is low, you want to pick it very bright color. So it's in opposite ways, but that's only apply when the multicolor panels is co-expressed. If it is expressed in a separate cells or the marker is exclusively separate in a different conditions, so you don't pay much attention to these rules. And also you want to design your panel with the limitation of our instrument. So you don't want to copy a instrument from other institution, then follow every design detail, then want to apply to our institution machines. Sometimes not apply because each institution have different machine settings. So the panel working very well in the other institution not necessarily works as well as in our machines. So even you follow all these rules, there are still issues we have to face. One is like the real population gate not clear. So sometimes you don't even see the population stand out of the negative population or debris. Or the data is not aspect is not as good as you're expecting. So the first one, I'm going to show you an example, which is provided by BD. It's showing a co-standing with two markers. One marker is CD3, another marker is CD197. The first, the top row is using a bright fluorophore or bright dye conjugate to CD193. The low row is conjugate to a dim dye. So you already can see the difference. The top one use the bright dyes. We can make this population more separate compared to the low row with dim dye. So that's an example showing you the impact of different dye will impact on your result. So all the manufacturer, when they provide their conjugate dye to their antibodies, usually they will telling you how bright their dye is. Here is an example, which is provided by BD, and showing you some dye is considered very bright, some dye is bright, some dye moderate, some dye dim. So you also want to pay attention to the lasers. So here, list 5 lasers. Some machines do not have all these 5 lasers. Sometimes machine only have like 3 lasers, sometimes machine have 4 lasers. So the same dye, for example, P, it can be very bright, shine by the yellow-green laser. But if your machine do not have yellow-green laser, it usually will be shined by the blue laser. Then the brightness of the P will decrease. So it's, and we have a website called Flow Finder. I will talk into that later on. I design. So it's a very helpful tools, which also lists on our call home page. So whenever you go there, you pick up the machines. We have a link to that machine and list all these parameters, all this dying. So you will design help you design a panel. I will do a demo after this presentation. So here is a very busy slide. You don't need to worry too much. And here is give you an example showing you how we define our target into mostly like 3 categories. First one we call this primary antigen expression, such as CD3, CD4, CD19. So this is a well-defined. Usually, if you stand antibody with this antigen, it will show you very clearly negative population and positive population separated very well, regardless which color you are conjugate to your antibody. And secondary is such as CD27, CD45RA is also well defined, but usually it's expressed not very well separate. So there are always something in the middle between negative and positive. So we call this secondary. The third one is tertiary, such as CD25, FOXP3. So this one usually expressed at low levels, but it can be changed expression levels upon like activation or the stimulation. So when you pick your antibody and the colors, you have to considering, are you looking for like normal low levels or it's after activations? So you have to considering this to pick out your brightness of your colors. So here the figures is from this paper I just found, and it's showing you all these three category antigen level looks like in the slides. Something like a CD3 can see a well separate negative positive. Secondary CD27, which is can see negative positive, there always something in the middle. And the CD25 is usually have something very low. And let me see where it is. Usually this one, TNF alpha also we think it's a low level expression. So after you pick up the colors, I have lots of users come to me. I looked at their protocols. The most thing I think is adding 1 to 100, 1 to 200 dilution of your antibody to your cells. But then I ask how many cells in your solution. Most of people don't know. They don't even count. So that will be a big problem. So to solve this problem, I want to introduce another term. It's called a STAN index. So when you're doing your antibody titration, this is the parameter you want to calculate. So STAN index must be done one by one for your single color before you doing multi-color panel. You will do 5 colors. You have to titrate all 5 antibody one by one. You also have to make sure all antibodies perform the same way when you combine them together. Because some antigen you're looking for is really close to each other. When it's stand one by one, it looks okay. But when you mix them together, one antibody bind to the antigen will block the space the other antibody coming. So that way, the antibody is not going to perform the same way you stand one by one. So you have to make sure your cocktail is performed the same way for the single antibody. So then you have to do a validation after you determine your titration. So to do the STAN index, I give you an example here. So 1, 2, 3, 4, 5, 6, 7. So you have 7 tubes. Each tube you should have the same cell concentration, same cell working solution volumes. Then you're adding this different amount of antibody. Then you run each tube into the machine. So each tube will give you a result looks like this. We have a negative population. This is the histogram, negative population. Then we have a positive population. So from these two populations, we will have mean fluorescence. From the negative one, we will have mean fluorescence. From positive one, we will also have a standard deviation from the negative population. So here is the formula we're going to calculate the STAN index for each point. So then we plot this every STAN index value against this amount of antibody, we get a curve. So we're looking for the highest STAN index, which is here is the amount of antibody we're going to use for the next protocol. So if we use less antibody, the signal will be very weak. So maybe we're considering the particle ratio will be here. That's why your stand index is low. If we're adding too much antibody, what's going to happen is it's no longer further increase this particle ratio signals, but will expand this negative signal due to non-specific binding. So it's also cause decrease of the stand index. If you also add too much antibody, of course, you will spend too much money to bind antibody. We don't want that to happen. So less or too much, both decrease the stand index. So you want to optical this stand index, the volume. So the next step is you load your tubes and adjust the PMT voltage to put your population in the range. So it's recommended by the BD where is the best PMT voltage you want to put. So here is the formula you want to follow. So when you adjust the PMT volume, make the negative cell robust, stand deviation is bigger than 2.5 times of the robust deviation of the EN stands for electronic noise. So each channel of electronic noise we can directly read from our performance report. Now we just do a simple calculation, 2.5 of each channel. Then we adjust the PMT for each channel. Here is so first of all, we want to know what is the robust means. Robust statistic is a method to calculate. So here is a formula to calculate the robust standard deviation and robust coefficient variations. So here example how this robust statistic works. So if you run the flow, you will know besides your normal majority populations, there are always few outliers. It could caused by like machine errors, electronic noise. So it's beyond our control. So this robust statistic is try to eliminate this effect of these outliers. So after the robust deviation, we can see the first column, the calculation is without this robust calculation. So the total variation will be 128. Within P2 gate is 38. But if we apply this calculation robust, so the both whole things and everything in the P2 will have a same variation. So that's the purpose for the robust deviation. So let's back to the PMT settings. So here is an example, and we want to set the PMT voltage for this physics detector. We already know the robust standard deviation for the electronic noise is 20. So 20 times 2.5 is 50. So we want to our standard deviation, robust standard deviation of this negative population is bigger than 50. So we try this 3 voltages. First voltage is 370. We have this parameter. Stand index is 15. This one is 25. So this one is not good. So now we're going to 470. So stand index increase from 15 to 39. We also have this robust stand deviation of negative is going to 64. So it's higher than 50. So if we continue to increase the voltage, the stand index increase a very little. So it's also push the signal to the end of our linear range. So if we push too much, all the signal above 10 to the fifth, we think is out of range. So it's not comparable. So This one, the middle one, is the best voltage we want to use for our experiment. So that's why I have the expand to this one. So after we set the voltage, next problem is when we do more than one colors. Here I have an example. We have one cells conjugate two colors. One is Physi, one is PE, which are both very popular colors for flow. This figure is we call spectrum. So the x is the wavelength. The y represents the relative intensity of the light. So 488 is the wavelength is a popular blue laser. So both Physi and the PE can be excited by these blue lasers. After excitation, this curve represents the emit light from the Physi. So the Physi emit light will be ranged from 488 all the way to 650, the wavelength. And the PE will emit a light from 550 all the way to more than 650. So this square represents our bandpass filter. So there's a number 525/50, which means the middle of the position of this filter is 525. The width of this window is 50. So this filter will allow any wavelength in the middle going to pass and block wavelength lower and wavelength higher. Again, here is another wavelength filter. So this two wavelength filter, the purpose is try to cut off the other light is not from its line. So the first one, we put this first filter before the detector of the Physi. We put the second one before the detector of the PE. But the problem is you can see this tail from the Physi, this part, still get into the filter of the PE, right? So here is there are some numbers, so I can explain what the number means. So let's say our cell conjugate to the Physi and excited by the 488 is emit a Physi light. So if we considering this whole curve, the whole green curve as a 100% of this emit light. So this 71.5% is where this filter will be allowed this light goes through. So whenever there's 100% of the Physi, 71.5 light will go passing the Physi filter to reach the Physi detector. That's the 70.5% means. This one, this part is 11.8 out of this whole curve will reach the P detector. So let's first assume there are no P at all. Only one Physi light goes through. Both detector will get signals. The Physi detector gets signal is from this 71.5% of the Physi light. The P detector also gets some signals. It's from the 11.8% of the Physi light. So that's we call it overlay. So if only one fuzzy light goes through, both detectors will get signals. It's 71.5 and 11.8. They're the ratios based on this filter setting. So the ratio will be do a calculation. In this case, is 6.5%. So then, because this fuzzy can be higher, can be lower. Whenever there is a fuzzy signal showing up in this detector, we will tell there must be another 16.5% signal will be showing up here. That's the ratio for the purpose for the compensation. So today we are not pay too much attention to the compensation because that's another topic. If you really want interesting or you get really confused on these slides, we can find another time. We can give you another seminar only focus on the compensation, how the compensation works. But this slide's purpose is showing you what happened or what's the mathematical base for the compensation because of this overlay, or you can call it overlap or spill over the light from one dye into the other detector. That's the mechanism behind this. Also, there is a ratio, fixed ratio. So when we have these ratios, the machine can do a calculation to subtract this part of the ratio to make things correct. So people says, okay, how about lower the filter? Okay, we can actually use a narrowed filter, but we can still, the overlay is still there. So there's no way to going around. So we have to do some calculation to do that. So here is what happened when we do the compensation. So here we have negative populations, we have fuzzy positive populations. Let's look at the middle part first. Before we do the compensation, because the fuzzy light have some spillover or overlay into the fuzzy, into the PE channel. So if we put a threshold based on our negative populations, so this fuzzy alone positive population will show some, looks like a positive for PE because the overlay. So then the machine will do some compensation to subtract a certain percentage of the fluorescent intensity. That's what happened here. So after compensation, how do we know? How do we tell the compensation is correct, have been done? So we can look at the mean fluorescence of negative population on the PE, 77. After compensation is 74, so it's very close to match. So we know this one is done. Before the compensation, the mean fluorescence of PE negative is 72. This one is 200, so this one is much higher than this one. We know it's not compensated well. What if we do too much compensation, or in other words, subtract too much? That is happening. So 70, this one is already minus, so that's lots of events have dumped to here. So this one called overcompensate. So either way is not correct. Only this both populations match. That's the correct compensation. So what can cause the problem? Either overcompensation or less compensation. People using different floor plan for use. For example, their positive cells, the experiment positive cells is GFP, but they using fuzzy for compensation. That will cause problem. And also they use a negative and positive population have different autofluorescence. For example, they run the negative population as a cell. Then they don't have positive population for the antibodies, and they use some beads. So they mix the cell and the beads will cause a problem. So for do a right compensation, you use either use all cells or you either use all beads. Do not mix them together, otherwise you will have problem. So I have an example here. So there are two color compensation. One is V450, another one is PSI 5.5. You will use both cells for compensation. So it looks good. But if you use negative ones with cells and positive control for cells, after do the compensation, you run your samples. It looks like this. So this is end the compensation. So it should be bring this population further down, looks like this. So this one will be mean fluorescence of the 450 of these two populations should be the same. As we know, this one is good compensation, this one is bad compensation. Okay, so next is, so first of all, we have to tell this one is good compensation. So then what's the problem? So this, I put a small population here. That's before compensation. After compensation, so the whole blue population is moved down here. So usually we run our fluorescence plot in the log scale. So see, this is 0, 10 to the 4, all the way to 10 to the 5th. So log scale is different from linear scale. If one population is located here, so we can see it's spanned from the about 1,000 all the way to 4,000. So it's spent like around 2,000. So the mean fluorescence is about 3,000. So that's why it's located here. So the robust SD is 209. So after it's did a compensation, it's moved down to here. So remember, this is a log scale. So the same thing, 3,000 will be, looks like much bigger than on the higher levels. So the robust standard deviation is still the same thing. The mean fluorescence decrease, but the problem is this population is get expanded. So if we have a cutoff threshold based on negative ones, this part will be looks like positive for this P size 7. So why that happens? Previously we look at 2 color spectrums. Now we look at 4 colors. We're increasing to number 4. So again, this is a similar. This each curve represents the emission light of this excitation. So 50 PE, P text red, P psi 5. So that's the whole spectrum of each light. This score is represent the range of the bandpass filter. That's the numbers I just explained on the previous slide. So if you have further questions, we can organize another seminar when we do the compensation. The purpose for this slide is showing you we looking for the let's see, we look at the P and we look at the other three colors. So that's the P. P have very, very few overlap into the fuzzy channel. That's why we increase the brightness of the P. There's really not much we will detect particle for fuzzy. And we look at this tail, it's like very big part, this part, overlay into the P text red, or we can call it PCF594, that's the same thing. So we increase the P signals, we can also see a significant spread over into this channel because that's the overlay. So it's also have a tail get into this channel, P side 5, which is this part. So this part obviously is smaller than that one. That's why we increase the intensity of P. This signal is decreased. Not as much as this one, but still higher than P. So that's, we call this phenomenon spillover. So why we worry about spillover? Because spillover will decrease the resolution. So remember, we just mentioned the stand index, right? So stand index represents the separation of the negative population to the positive population. That is a very good separation. But if we do a compensation, of course, this is a good compensation. We can tell because this mean fluorescence looks like match to the levels. So because this spread, this separation is decreased compared to the one we just one colors. So that's called loose resolution. But if we can keep the result looks like this, everything's still okay because there's still a good separation, even though the stand index is decreased by 50. But in reality, that's not always the case. Here is an example. So sometimes we will have a very dim double positive population, looks like here. So if we have this population spread, sometimes even get into here. So there's no clear cut. We can tell whether there is a double positive population because of this. If the population on the P8 is very dim, sometimes totally buried into this single particle, so we cannot tell whether we still have a population for double particle. So how do we resolve this? There are three ways we can resolve this. First one, we titrate antibody. So we bring antibody for this color a little bit less. So it's when the intensity of this antibody signal gets dimmer, so the spillover will become less. So we'll see this population more clear. Another way is we change a more bright color for this antibody. So hopefully we can bring this population up. Usually that's not available for us. Another way is we can keep the antibody position there, but we choose a less spillover dye. So that way we can make this antibody population more stand out. So here's another example to showing you how the different dye give you a different result. So the experiment is doing a CD28 and the CD4 co-staining with two different colors. So CD28 is using this color, P side 5. And we use two different colors conjugate to CD4 to show the result, how it looks like. So CD28 alone looks like this, negative, positive. And the CD4 alone, QD655 looks like this after compensation. APC looks like this. So QD655 looks to have a more spillover compared to the APC. So if we use less CD4, so from this one to bring down to here, so it will cause less spread over. That's one of the strategy, titrated antibody. So after co-staining, you can see spread over close to this one, but if we use less, bring this population down to here, will make things separate. So that's one of the strategy how to work. But most of people don't want this result because we got better separation here. Now we get a worse separation from here. So it's not a good solution for the problem. So how do we pick the right colors? So here is a list called resolution impact matrix. So what this means? This is list all the detector of one certain machine. And this is not calculated. This is actually measured one by one by the BD engineer. When they build this machine, they run each single color beads to measure the spillover of each color. So the red color means these two colors, if using all together, will cause the stain index lose more than 80%. So that means your resolution will totally messed up. So the pink one will be 60, between 60 to 80. So the green one is the best, almost nothing lost. So the more red color, for example, this one, BUV 489 and the BUV 59. So this one not even coming with the same lasers. So this line is more excited by the UV laser. This line will excited by the violet laser. This still cannot be used all at the same time. So I just randomly check the internet, find publications talking about Treg. So hopefully some of you doing the Treg works, so I can use this as an example to showing you how we can optimize our experimental panel design. So this is I just random pick up a public data from this paper and is try to identify the Treg from the samples, which is CD25 positive and the CD127 negative. So this set of data is provided by BD and for education purpose. So in this panel, we want to identify the Treg cells, which first one is use CD8, CD4, identify the CD4 T cells. First of all, they go through the CD3, screen the T cells, then going to CD4, CD8, looking for CD4 part. Then out of CD4, they're going to either looking for CD45RA and CD25. They're also looking for CD127 and CD25. So the first panel, the first row is use just whatever the antibody is available. Do not consider anything. So that's the final result. It's very similar to the publication result I just shown you. So remember the first rule I just mentioned. When you pick up the antibody, you always want to match the expression levels and the brightness in the opposite way. So we know in T cells, CD3 and CD4 is usually highly expressed. So P is a relatively bright dye. So you do not want to use bright dye to the highly expressed level markers. So that's the second panel. So we try to match in the opposite way. So we use the Physi for CD3, which is a dimmer color. We use this one for CD4, which is also a dimmer color. Then we use P, which is bright, for CD25. So this way we make CD25 looks like better separate compared to this one. But still, we don't have a very good resolution for the Treg cells. So what we can do improve this. Before I going to continue, want to introducing one more concept. It's called mean fluorescence. Fluorescence -1 FMO controls. So by word, you can know fluorescence -1, which means you will have 3 color panels. -1, you always stand sample with 2 colors. The purpose for this one is to see without these colors, how the other color will impact the threshold of these channels. This example using 3 colors, Physi, P, and P psi 5.5, and it's looking for a T cell, T memory cells. It's only give you a plot Physi against P, but we already know there is another color. It isn't showing up here. So first is the N-stand plot. So if we plot a gate based on this N-stand, will be like this orange dot. So the second plot is FMO. FMO means for this case, the sample only stand with Physi and P psi 0.5 without P. So we can see the signal compared to the N-stand. You based on this gate, almost everything is considering P positive, but we do not have P here. So that's why we drew another gate of the FMO boundary here. So when we run the 4 panels, now we know this is the real P positive. This one is not. So that's how the FMO works. Now we're going to do our own Treg panels. Here is the resolution matrix. We look at the original color we used. We found the per CP psi 0.5, which is here, and the P psi 7. Boom, is red. So that means these 2 colors cannot be used together in the cell. So it's helping CD4 and the CD127, which is we are using all together, looking for the panels. So then we're doing a FMO. We don't use this CD4. We don't stand the cell with CD4, but stand everything else. That's called a FMO for CD4. After we subtract the CD4, we can see more clear populations here compared to the 4 panel. So this one is the 4 panel. We first gate out of these cells, then we show up here. This one we only gate this one, CD8 negative, everything CD8 negative is showing up here. So this means this per CP sign 0.5 has something to do mess up the signals. So we have to change. So the first thing we do is we swap this one to CD8 because we are not going to see CD8 for Treg. It's not co-staining, so we put this color in trouble to the other type of cells. So we swap this out. This one keeps the same. And F640, 647 is more bright than APC, so we use this one. So after we change this one, that's the final result looks like. So in comparison, that's the first pen. You just use whatever the antibody available. We got a result looks like this. The second panel is we're considering to match the antigen expression level with the brightness of the color in the opposite way. That's how the result looks like. And finally, we have considering the spillover of all these colors, then we get a very beautiful result. So that's how you choose different colors will impact your final result. And also, you want to monitor your flow. So some experiments record over 1 million cells. It takes a very long time to record each sample. So it could happen in the middle. There are some bubbles, there are some clogs go through the machines, disrupt the flow of the samples. So on the left is a good flow, so there are no disruptions, so you can trust your result. On the right, there's something disrupt the flows. So if that thing happens, you can imagine this at this time, the other rate will generate a P5 signal around 10 to the 3, but at this time it will generate a signal around 10 to 2. So it looks like in your plot will looks like two populations. Actually, that's not real. It's because your flow gets disrupted. So that's also one point you want to keep eye on. Okay, so we already talked about the overlay and the spillover. So what we can do to improve? So right now, the company is trying to manufacture some new dyeing. It's going to narrow down the emissions, so hopefully can resolve. Also, it can replace the fluoroforms with the metal isotype called mass spectrum flow. We also, you maybe also heard about spectrum flow. It's not only measure the one part of the spectrum, it's measure the multiple part of spectrum, but still need a compensation. Okay, the last one, I will show you some useful tools. So you will go to our, the home page. So that's our, when you're going to the iLab, go to our homepage. That's where you can see, we list all this equipment in the homepage, and under each equipment, you will see a link, view machine settings and design panels. For example, you will want to use this machine, you click the link. It will open a web page called a Flow Finder. So first of all, this is the settings this machine has. Which kind of lasers, what kind of filter, and suggest color it for this machine. We will want to design your experiment. You click this button. So here is the options. For example, you can type any markers you're going to measure. For example, CD3, Then you can choose either human, mouse options. If the human, so pay attention to here. Before I choose the antigen density, it's list all these available antibodies for this color. But if I going to tell the software my antigen is a highly expressed antigen, so it will automatically block the bright color, only give me this option for dimmer colors. If you don't know, really don't know the marker, you are going to just leave like this. So it means all options available for you. So you can pick the antibody in the next step. So then you go back to the ones you really don't know the expression level. So I think my time is almost there. So any questions, you can send me an email. So I will help you design your panels. Any questions, just email us. We are happy to help. Okay, I think that's it. Any questions?
Thank you so much, Dr. Yu, and it's a very nice presentation. And yeah, like person can answer like open for session, and you can ask the questions, please. Dr. Yu, I have a like one question about like a stain index actually.
Hmm?
A stain index.
Okay, let me bring that. Okay, I think that's one, right?
Yeah, yeah. So like in the stain index, like there's a line graph. So if it's showing like a 0.2, it's like a and 0.5, right? So it's like a 2 point we have here. So it's mean we can choose that concentration for our like our
Yeah,
experiment,
you can choose either concentration or something in the middle.
or like a mean, like a
Yeah,
mean. Yeah. Okay. Thank you so much. Yeah. This is the only one. Uh, Dr. You people are asking like if you can share this presentation with us.
Yeah, I think you already recorded, right?
Yeah, yeah. I'm going to record. Yeah, it's already recorded. So I'm going to share this one to everybody in the Jefferson. Yeah. Thank you so much. I don't think so. People they don't have any question yet.
Yeah, if you have any question in the further future or you want to help the user flow, just contact me directly.
Yeah, sure, sure, sure. Thank you so much.
Bye.
Bye bye.